I welcome you all to the topic magnetic field intensity H vector due to infinitely long coaxial cable. That is, in order to find out the magnetic field intensity for a symmetric structure, we will be applying Ampere's circuital law. According to Ampere's circuital law, the magnetic field intensity across a closed loop is equal to the total current enclosed by that loop. Another one point what you have to remember here is Ampere's circuital law can be applied only to symmetric structures. Here I have considered the application for coaxial cable. So this is the coaxial cable. Coaxial cable is nothing but a transmission line used to carry high frequency electrical signals. That is, the structure of the coaxial cable is we have a core. Surrounding the core is a cladding of certain thickness T. Here A represents the diameter of the core, B represents the there is a radius of the cladding. A represents the radius of the core and B represents the radius of the cladding. B plus T represents the thickness of this cladding surface. So here we are going to find out the there is a magnetic field intensity in 4 particular regions. There is this coaxial cable can be oriented into this diagram is useful for that is explaining the 4 possible regions of a coaxial cable connector. Okay, so here we have a core region and this is the cladding region. There is inside the core region we have a certain Amperian path. There is then in between the core region and the cladding region there is another Amperian path, and in between the there is cladding region of certain thickness T, there is an Amperian path, and there is outside of the coaxial cable also we have an Amperian path. What you have to remember here is the direction of current entering the cable is opposite to the direction of the current leaving the cable. Okay, so consider this is the direction of the current entering the cable and this is the direction of the current coming out of your coaxial cable. That is, for easy derivation purpose, we have to divide your coaxial cable into 4 particular regions. That is, the first region corresponds to the core surface. That is, the second region corresponds to the region between the core and the cladding. That is, and the third region corresponds to the region between the there is a cladding and the thickness of the cladding B plus T, and the outer region is there is a radius greater than B plus T. Here I have used the term rho in order to represent the radius of this Amperian path. Okay, so as I said earlier, for each possible regions you are going to find out the that is a H vector with the application of Ampere's circuital law. Okay, so let us discuss for this region 1. As I said earlier, this is the equation for Ampere's circuital law. Integral over L H dot dl is equal to I enclosed. We all know that the current I can be represented in terms of current density as integral over S J dot ds. J is nothing but current flowing across a particular unit area. Okay, so that is represented by J. So therefore I have written J is equal to I by pi r square. This is the area of the circle. Here, as the radius of your core is A, I have used the term A square instead of R here. Okay, so this AZ represents the direction in which your current density is present. That is, and for this ds I have written this term rho d rho d phi into AZ vector. This is based on the coordinate systems. Okay, here we have used a particular coordinate system, and according to the coordinate system ds is written like this. Okay, so next, first let us solve this term. I enclosed is equal to integral over S J dot ds. First let me find out the value for this I enclosed. Next step what I am doing here is I have derived my J as I by pi a squared into AZ vector. I have to substitute that. As it is a constant term, I have taken it outside, and inside my integration I will be having my rho d rho into d phi. We all know that the angle of phi ranges between 0 to 2 pi and your rho ranges from 0 to rho. Okay, so the next follows an integration process. I am integrating this rho. Upon integration it becomes rho squared by 2 over the limit 0 to rho, and when I integrate this d phi I will be getting phi over the limit 0 to 2 pi. So therefore I have got 2 pi here. Next thing, I have substituted my limits, and finally I got the value for I enclosed as I rho squared by a squared. Okay, so next thing what I have to do is I have to substitute this in my integral over L H dot dl. So this H dot dl can be expanded as H phi into a phi vector, because there is phi is along the there is H is, that is magnetic field intensity is along my phi direction. this is along my phi direction. So therefore I have represented the term h phi into a phi vector. dl is expanded as rho d phi into a phi vector, which is equal to I enclosed what we have solved here. Okay, so upon solving this, we know that the range for phi ranges from 0 to 2 pi. So finally I have got my h phi term, and that's equal to I rho by 2 pi a squared. So for this region 1, that is the magnetic field intensity, what I have derived is h is equal to I rho by 2 pi a squared. Next, what I have to do, I have to solve my magnetic field intensity for this region now. Okay. Next, we will derive the there is magnetic field intensity for this region 2. As I have said earlier, there is region 2 is a region between the core and the cladding. That is, therefore, this region is considered as A less than or equal to rho less than or equal to B. What does rho represents? Rho represents the radius of your Amperian path. Okay, so similarly, I have that is obtained my Ampere circuital law equation, integral over L h dot dl is equal to I enclosed. That is, here what you have to remember is there is the region between core and the cladding is much similar to the that is infinitely long conductor placed along z axis. The coordinate system what we are considering here is your cylindrical coordinate system. That is okay. So as this is the case, already that is we would have derived for the magnetic field intensity due to infinitely long conductor placed along z axis, and therefore I have substituted this h phi. H can be represented as h phi into a phi vector. The differential length dl according to the cylindrical coordinate system is represented as rho d phi into a phi vector. So therefore the integrating term here is your there is d phi component ranging over the limit 0 to 2 pi. So here the I enclosed is equal to the total current I, which represents this. Upon solving this, I will be getting h vector is equal to I by 2 pi rho. I hope you are much familiar about this. Why I didn't use the term vector here is, here itself I have represented the direction. Now, if you are going to write this in h vector is equal to I by 2 pi rho into a phi vector. This is how you have to denote. Okay, so next we will be solving for your region 3. Region 3 calculation will be a bit complicated when compared to the other two regions, but we will solve this. That is okay. The region 3 is the region between the there is a cladding and the thickness B plus P. So therefore its radius ranges from B less than or equal to rho less than or equal to B plus P. That is, I have obtained my Ampere circuital law equation. There is next step what I have to do here is I have to remember this term. I enclosed, we normally know it is integral over S J dot ds. But for this region, that is I is equal to I plus integral over S J dot ds is your enclosed current. This condition you have to remember here. This is applicable only for your region 3. That is, therefore, first I will solve this term integral over S J dot ds. But here obtaining J itself is a big concept. That is, just clearly understand, my dear students. That is here why I have represented the term minus here is minus represents the opposite current when compared to the inward current. Therefore, I have written minus I here divided by pi into that is a pi r square, the same concept. Here the radius I have defined as b plus t the whole square minus b squared into a z vector. Then ds, differential surface according to the cylindrical coordinate system, I have written here. That is, therefore it is this. Okay. Then what we have to do, we have to substitute this in this equation. So therefore, I am finding my I enclosed current here. I am having two limits. There is one corresponding to d phi and the another corresponding to d rho. So therefore, this term I have taken as a constant outside. Minus I by pi into b plus t the whole square minus b squared has been taken as a constant term. And inside this integration, I have my term rho into d rho into d phi. Okay, so you all know the limit for d phi ranges from 0 to 2 pi, and here the limit for d rho ranges from b to rho. Okay, so then what I have done, I have integrated this d phi. D phi upon integration will become phi over the limit 0 to 2 pi. Okay, we all know that. Next, when I integrate this rho with respect to d rho, what it will become? It will become rho squared by 2. Okay, so for this rho squared by 2 over the limit b to rho. Okay, that's what I have done here. This is the step applied here. Then I have to substitute my upper limit minus lower limit. I have substituted here rho squared by 2 minus b squared by 2 into 2 pi I have substituted. Okay, so the next thing what I have done, I have taken the LCM for this. That is, upon taking the LCM, next step what I have done here is I have brought this constant term outside. Okay, so minus I into rho squared minus b squared. Another one step what I have similarly done here is I have expanded this b plus t the whole squared. Here you have to apply this concept. A plus b the whole squared is equal to a squared plus 2ab plus b squared has been applied here. Okay, according to this b squared plus t squared plus 2bt minus b squared. So what will happen here? This positive b squared and negative b squared will get cancelled. So therefore, I will be getting minus I into rho squared minus b squared divided by t squared plus 2bt. What is happening to this pi? There is this pi and this pi will get cancelled. Okay, so then this 2 and the denominator term 2 will also get cancelled. So finally, I will be getting this as my equation for integral over s j dot ds. Minus I into rho squared minus b squared divided by t squared plus 2bt will be my final term. What I have already said you, this I enclosed is equal to I plus integral over s j dot ds. Now we have found out only this portion. Next what I have to do, I have to substitute this here. So therefore I minus sign minus I into rho squared minus b squared by t squared plus 2bt. Next thing what I have to do is I have to take this I as common now. That is upon taking this I as common outside, then what I have to do, I have to substitute in this Ampere circuital law equation. So totally my I enclosed will be like this. That is if I taking this I constant outside means 1 minus what it will be here is 1 that is I taken outside that is no I taken outside now minus rho squared minus b squared by t squared plus 2bt will be the term here. Okay, so both the terms are that is 1 minus will be here. This I taken outside 1 minus rho squared minus b squared by t squared plus 2bt. The next thing what I have to do, I have to substitute here. We all know how h can be expanded. That is a h phi into a phi. dl can be expanded as that is rho d phi into a phi. The same thing you have to apply here, and for this I enclosed you have to substitute this. Upon solving all this, finally we'll be getting your h phi as like this. That is you can solve and see final expression will be like this. Okay, so this is for your region 3. For region 3, first you have to define this integral over s j dot ds. This itself you have to remember here. Next thing what you have to carefully look upon is I enclosed is equal to I plus integral over s j dot ds. That will be your enclosed current here. Next we are coming to the region 4. As I said earlier, this region 4 is the region outside your cladding surface. So therefore the radius is rho greater than or equal to b plus t. That is the outside current. That is the outside current. In order to calculate the outside current, we have to calculate it as I in plus I out. From the initial lecture itself, I have said you the direction of the incoming current and the direction of the outgoing current will be opposite to each other. So therefore, what happens? Input current and your out current will get cancelled each other. So completely your I enclosed will become 0. So therefore, we cannot have the magnetic field intensity outside your cladding region. So these are the 4 regions. From these 4 regions, finally what you have to do is you have to draw a plot. That is what does that plot is going to represent to you is that is the so finally you have to plot a graph between that is the radius and your magnetic field intensity. What you can interpret from this graph, r is equal to a represents the radius of the core, this represents the radius of the cladding, this represents the region between, r is equal to c represents the region between that is cladding and thickness of the cladding, that is your b plus t, and this region represents the outside of the cladding. Okay, so what you can interpret here, the magnetic field intensity will be high near the core and it will start decreasing in the region between the core and the cladding. Further, it will decrease in the region between that is b and b plus t, and for the radius greater than b plus t, magnetic field intensity will become 0. So this interpretation you have to finally make and you have to plot this graph. Okay, now I hope you have clearly understood how to obtain the H vector, that is your magnetic field intensity due to infinitely long coaxial cable. First thing what you have to do is you have to divide the coaxial cable into 4 different regions. That is for these 4 different regions you have to find out your that is H vector acting along your phi direction. Okay, So since magnetic field forms a closed loop, we are considering this there is phi direction. Okay, so this also you have to concentrate. Finally, you have to stop with this graph. Thank you.